Let us start today's session. Good evening, everyone. Welcome all of you for this ninth week live session for the Smart Grid Basic to Advanced Technologies NPTEL course. Welcome all of you. We will start with today's session now. Okay. So I am Gagan Meena and I am a fourth year PhD student in Electrical Engineering Department at IIT Bombay, and my specialization is power electronics and power system. Let us start. So we will be discussing today the overview of week 9, and we will discuss certain questions and then topics related to those questions, and then doubts regarding this week 9 material or any other week material which you want to ask. You can ask doubt in between also after the session. Just to remind you, the deadline for assignment 9 is March 26th, and deadline for assignment 10th is till 2nd. Please submit the assignments on time. Now, and I hope all of you are able to access the recordings of the live sessions and the material which TAs are used for the live sessions. Both the links for the recording of the live session as well as the link for this material which is being used for these sessions is available on the problem solving sessions tab. And there you can find the Google Drive link for the material as well as the YouTube recording link for each and every session. So you can go through this URL link, or you can go to that Google Drive sheet. So let us begin with the overview of week 9. And starting from this week 9 onwards, we will be discussing regarding the demonstration of the theoretical aspects which have been covered till now, till the week 8. Whatever concepts we have developed, we have discussed till week 8, their demonstration, small scale demonstration using hardware setup will be explained in the subsequent weeks, starting from the week 9. How? Because once we, first stage is the development of the theoretical aspect, right? Development of the theory. Then we have validation using simulation. Then we have a using small prototype, okay, hardware. So we have studied this, and in this course we are not studying how to simulate all these things. So that requires coding things or simulating or drawing the models in the relevant softwares such as Simulink available in the MATLAB, or you can use PSCAD or RSCAD. All these things you can use. So that is a simulation aspect. And once we are able to verify the observations which we have derived using theory, once we verify those observations using simulations, then we can confirm that yes, this is working as intended. But that simulation verification using simulation or validation using simulation is not sufficient, because there are many practical aspects involved while we try to do that same simulation on a hardware prototype. Because you may say the theoretical, while calculating the values of L or C, it's an example. Let's say we are designing a boost converter. Let's say we are designing a DC-DC buck converter, and for that we need to find out the value of L, C, right? Let's say the value of L comes out to be 5 millihenry. Not 5, let's say 5.39 millihenry. And now when we want to design this as on actual hardware, we might not be able to get a 5.39 millihenry inductor. That is not possible. That may not always be possible. You might get a 5 millihenry inductor, 5.2, even 5.3, but not 5.9 may not be possible. That will alter the results a bit. So we need to make those adjustments and check how what are the results after these small variations, differences from simulation and the actual availability. Then there are also issues of noise while we are using different measuring instruments per probes. And there are issues of noise, and then not, the elements are not ideal. The analysis which we do, the theoretical analysis which we have done, that might that is that might be involving many assumptions. Not all the non-linearities, not all the non-linearities are captured in that model, in that theoretical model. But when we are practically trying to do the same thing on hardware, those non-linearities will come in. That why is this not working in the same? Just a minute. I will share the PDF now. Okay. Just a minute. I will just share the PDF with you. What we were discussing is that while we are trying to replicate that simulation on actual hardware, there are many difficulties, there are many differences due to noise, due to the mismatch in the actual component which is required and which is available. There is a difference between the two. Then there is noise as well, and we might not get the same results. Little bit non-linearities and non-idealities are there that we need to take care. I hope it's visible now. Okay, let us. Yes, I think it's visible now. Okay, so we were here. That one is the theoretical aspect, then validation using simulation, and then validation using the actual hardware. We need to validate everything using simulation as well as hardware. There's a difference between validation and simulation as well and hardware. There are many challenges. That's why the simulation, the results which we are getting in simulation, the exactly same result we won't get in the actual life. That's why we need to have a small prototype, and we cannot because everything we are going to connect into the grid, so we cannot even directly go and connect our DG or solar farm, wind farm into the grid, because we cannot do that without checking, without checking checks and balances, without full proofing that particular generator. We cannot directly connect it to the grid because grid is a very important, a very costly asset, and the reliability is of the most of prime importance. If there is some issue while integrating that renewable and there is loss of load or curtailment is there or some stability issue, then it will be a problem from the point of view of reliability, and that we don't want. So before integrating anything into the grid, we need to do extensive simulation and prototype studies. It is very, very important. And that we will see in the subsequent weeks also how can we do real-time analysis using these real-time digital simulators, LRT, all these things. By using these softwares or hardwares, we can mimic the actual behavior in the real world. In this week, the demonstration was for solar power generation, wind power generation, battery management system, EV charging system, and hierarchical control techniques in the hybrid AC-DC microgrid. Last topic we have already covered in the previous weeks also. Here again, the same thing will be repetition, so we won't go much into details of that. And above four topics, we have studied the theoretical aspect. We have studied the theoretical aspect for solar power generation. Let me write something. Okay. Okay. We have seen that. This is the photo-generated current which goes, part of it goes into ID and ISH. And this is the final current. And we have already seen that we have this PV curve and then this IV curve. And we want the system, the generation, the PV plant to operate at this maximum power point. Even when the irradiance changes, we want to track this maximum power point when the irradiance changes. Because we want to derive the maximum out of the PV at a particular insolation and temperature. Otherwise, we can operate at this point also. But we don't want that. We want to extract maximum out of PV. So we can use that excess generation in charging the storage, and which can be used to meet the demand during the absence of these renewables. During the night time when the renewables are not present. If we want to get the maximum out of PV, extract maximum from PV, and this is point where it will operate at maximum power. And this is done by the buck, that boost converter, the chopper, by changing the firing duty cycle, we can do this change. So this is demonstration. So this was theory of solar power. And because we want to operate at maximum power point, how we can demonstrate that same thing. What are the controls required in maximum power transfer? What are the different loops available? Different controls are there for controlling this, for controlling the solar power plant. That we will see, and then we discuss the demonstration of wind power generation. The curve is something like this. Here is power and here is velocity. This is cut in. This is rated and this is cut out. Outspeed. The first point is demonstration of solar power generation. So here what we do is we use a programmable DC source which will work as our PV plant. Sorry. And this is that PV, that programmable DC source which is acting as our PV plant. And this PV, the output of this PV plant is connected to this grid emulator. It is an interface between the PV plant and the grid. And the control of the PV, the MPPT algorithm and other things, the firing pulses required for driving the IGBT stack or the gate driver circuit of IGBT. That control is designed in the Opel RT system. And the inputs which are required for control system are measured using the voltage and current sensors and circuit breakers. So we need to have the information regarding the voltage and current. What are the different values? And based upon that, the action is carried out. So here there are two stages, two types of solar inverter control. One is single stage and one is double stage or dual. So in the single stage, we have no chopper. The work of MPPT control that MPPT algorithm is implemented within the AC within the inverter itself. This is the MPPT block, which will generate the VDC link, the reference for the DC link voltage. And this is the actual VDC. Both these are compared, and this is the DC link voltage control. And this DC link voltage control generates the ID star, the active, the power and AC current control block. And that input are the D access current, reference and reference reactive power. And this will generate the PWM pulses for the DC to AC inverter. The power and AC current control takes input as the D access current reference and reactive power reference, the actual current and voltage. The PLL is used to sync with the grid. Here, this is the dual stage solar inverter where first stage is the DC-DC. Here we have direct DC to AC. Well, here we have two stages. One is DC-DC and this is the boost. Second is DC-AC. So DC and AC. The first one is the DC-DC converter control. Here we have the MPPT block. Input is input current, the PV current, and output is the reference voltage. And this is compared with the actual PV output. This is called PV voltage control, which generates the IDC star, which goes to the current control. PW. And this generates the PWM pulses for the gate driver circuit of DC-DC converter. Output of IDC goes to the DC current control. This so PV voltage control and MPPT. And second stage is the DC-AC converter control. Here we have DC link voltage control. We have a reference value, and then we get the real power. This will generate the PAC star. It calculates the AC current reference. Current AC current reference. So it's used to calculate the AC current reference, and then AC current control. Finally, the PPA is let us check this again. So what we have here is VDC links, the reference for the DC link voltage. And for the output of the DC link voltage control is PAC. The output of this is the PAC star. And then the AC current reference block. This calculates the AC current reference by taking the reactive power reference. And then the AC current control block provides the PWM pulses for the gate drivers of the DC-AC converter, whose output is the AC current and AC voltage. AC voltage superior goes through the AC current reference. So here we have two dual state solar inverter. One is the DCC boost conversion, and second is the DC to solar, the DC to AC conversion, second step. Now moving on to the demonstration of wind power generation. Here in demonstration of solar power generation, we had also discussed about two things. One was the Ripper reactor. In solar inverter, we did two things, right? I'm not able to recall. Yeah, there were two things. One is a rubber circuit and one is a bleeder resistor. The bleeder resistor is to bleed the excess charge. They remove the excess charge from the capacitor when it is not in use. And the snubber circuit is to protect against high dB by dt, high rate of change of voltage, sudden change in voltages. So for that, the snubber circuit is used. Okay. Now, brief introduction to the wind power generation. We've already seen this, but I will go through it again. So first, the kinetic energy goes through the wind turbine and it goes through gearbox to the generator. Gearbox is optional here. If the wind speed is high, then that's not a problem. But in most of the cases, especially in India, the wind resource is not of that good quality, and that's why we need gearbox. Then after gearbox is the generator, and after generator is the power converter. Power converter. After wind turbine, we have gearbox, and then after gearbox, we have this generator here. And after generator, we have this power converter, which is also optional depending upon the type of wind generation we are using. And then we have transformer here, which steps up the voltage level and feed it into the power grid. So here the initially kinetic energy goes into the wind turbine, which converts the kinetic energy into the mechanical energy by rotating the shaft. So this is a low speed shaft. And then here we have a gearbox arrangement which increases the speed. So this becomes a high speed shaft. And this high speed shaft rotates a generator which generates the output. Okay, so this was the arrangement for the wind power generation used in the laboratory, and we are using these type of uh, hardware setups to verify whatever simulation is carried out, whatever theoretical concepts have been developed. Everything is validated once we are able to do it alone. And so we have, before actually integrating a wind farm into the grid, we try to do that using a simulation and then using a small prototype. If both are working fine, then only we are able to integrate the wind farm or solar farm into the existing grid, because the grid regulator, or you would say the transmission company, whose the transmission corridor is is owned by the transmission company. In India, it's PGCIL, Power Grid Corporation of India Limited. It is between different states. We have the interstate transmission system. So that is handled by these the PGCIL. And whenever some grid integration is required, the generation owner has to it has to stick to all the requirements for grid integration. It should be able to meet those requirements so that it can be integrated into the grid. There are many requirements for the grid integration, which should not uh, make deteriorate the power quality in the grid. The integration should not affect the stability requirements. It should not affect the power system dynamics and control, as well as the protection aspect. So all these things need to be taken care first. And that is why, first of all, simulation is done in a small, then hardware analysis also being carried out, so that we can become fully certain that yes, this will work. So here what we have is a DFIG, double-fied induction generator, and it acts as this DC motor and the induction machine together. They act as the DFIG wind emulator, where the control of the DFIG is implemented in the WaveAct FPGA based controller. And then this DFIG is interfaced with the grid through this back-to-back converter. One is the rotor side converter and one is the grid side converter. So this is the control for the DFIG based wind emulator. Here what we have is the wind turbine here. Here we have the DC motor here which drives the induction generator. So because we want different wind characteristics, so what we do is we control this DC motor speed using chopper. The wind characteristics are emulated using this chopper. Here, what we have is how is this duty cycle generated for different wind characteristics. Here we give the input as wind velocity and pitch angle, and we have formula that half rho A VQ and into multiplied by the CP, the power coefficient, which depends upon the lambda and beta, tip speed ratio, and the pitch angle. The output is then multiplied by the rotor speed, and then we get the torque reference, which is multiplied by the motor constant. Then we get the current reference. We can compare it with the actual motor current, and then the converter, the PI controller tries to make the steady state error 0. Then we have the two converters, the rotor side converter and the grid side converter. Because of these converters, the grid side and rotor side converter, they are able to survive here. So we have the grid side converter as well as the rotor side converter as well as the grid side converter here. So here the rotor side converter, the output of both the converter is the firing pulses for the converters. These are the control logic. So this is the control logic for rotor side converter, and this is the control logic for grid side converter. This is the control logic for the grid side converter, and this is for the rotor side converter. Grid side and rotor side converter. This control logic will generate the firing pulses for both the converters. In rotor side converter, the NPTEL algorithm is implemented, where the input is the wind velocity and it generates the reference wind speed which compare with the rotor speed. And this is used to generate the current reference, which is compared with actual current to generate the voltage reference. So this is done for the Q axis. For D axis, the frequency reference frequency is compared with the estimated frequency, which provides us the current reference for the D axis. And then we have actual D axis current, and we take the reference, we get the Q axis and D axis voltage reference. And these can be converted into ABC domain. And these are given to the PWM generation for rotor side converter. Similarly, we have grid side converter where the reference DC link voltage is compared with the actual DC link voltage and is multiplied by the current reference by the PI controller to get the current reference, and it is compared with the actual grid side converter current, and then it goes through the PI controller and we get the reference voltage and D-axis voltage and D-axis Q-axis voltage, which is converted into ABC axes, and then it is given as the input to the PWM generator for grid side converter. The next topic was the battery management system. The battery management system plays a very important role. If the battery is not taken care of, then it can even burst, it can blast. So we need to take care of this battery. It is very helpful, but it is also difficult. So different functions of battery management system are monitoring of voltage, current, temperature, and the ambient temperature of each cell. Second is the online estimation of SOC and SOH, state of charge and state of health of the battery. Then we have this cell balancing, cell and module balancing, and this balancing can be active or passive. And the causes for the imbalance in the cell are two. One is temporary and one is permanent. So temporary is the leakage and self-discharge currents, Coulombic efficiency, performance, and operation, and uneven temperature. For the permanent case, it is the internal resistance, self-discharge, SEI, and the performance and operation. Then it also computes the energy and power limits of the pack. The demonstration was shown for the passive balancing of three lithium ion cells. So one is 300 mWh and 3.7 volts. Okay, so we have three lithium ion cells for, and we are going to balance these using passive balancing 3000 mAh and 3.7 volts. And the three cells are used of this rating, and a passive balancer IC of 20 ampere and 12.6 volt rating is used. So it provides a protection against short circuit overload, overcharge, and discharge. DC power supply, once the cell reaches its limit, mode 1 and 2 are activated in current. So in while charging, once the cell reaches its limit, the MOSFETs 1 and 2 are activated and current takes the resistive path. Once all the cell reaches 4.2 volts, the protection IC activates and stops charging. While in the discharging case, using the rheostat, MOSFETs 3 and 4 are activated and they deplete the charger cells. While so once all the cell reach 2.4 volts, while discharging, the protection IC activates and stops the discharging process. So this is the hardware setup for the active balancing using CHIL. So we have two things. Hardware in loop, we have two things. One is the hardware in loop and one is the computer or the CHIL. PHIL is power hardware in loop and CHIL is control hardware in loop. So we have a host PC here and then DSP connected to OpenRT. And so here we have the host PC, then DSP connected to our OpenRT, DSP to DI, and the digital input card, and then AO analog output card to the ADC. It also goes to the signal monitor to see how things are working. So then the input for the DSP is I1, I2, IN, SOC1, SOC2, SOC3, and D1, D2, D3. The final D1, D2, D3 are not input. These are the final output of the PWM pulse generator. D1, D2, and D3 are the personals. D1, D2, D3 are they have taken personal. So these will be used by the software if one is going to use. These are the output for the gate driver circuits. And the input are all the current values and all the state of charge values. Okay, let us go next. Next is the EV charging infrastructure. Here you can see we have four modes are available for EV charging infrastructure. The first mode is called as a electric vehicle supply equipment. It is permanently connected to the network, well mounted and commercial automatic charging station. This is a mode 3. Mode 1 is direct connection to the socket, no special safety. Mode 2 are portable chargers, special safety system in cable and public and domestic stocks. Here you can see four modes of charging: mode 1, mode 2, mode 3, and mode 4. Mode 1 is the most direct connection to the socket where there is no safety connection or safety aspect is not required here. Let me share the PowerPoint now. I hope it's going to work now. It's working till now, but I don't know how long is it going to be. Okay, so we're doing cell module balancing with active and passive. So once all these things are done, we need to complete energy and power limits of the pack. Yeah, about balancing using CHL, we will come into detail of CHL, but here I will say that what is being done is FPGA or in the Opel RT, the software of Opel RT, what you can do, you can create a simulating file, MATLAB simulating file. That software can integrate with MATLAB simulating file. You develop those files and send it to the user. So Opel RT, you create a simulating file and then give it so that it can be offered to the Lord. So what is done here is the input from the input goes to the digital input, and from ADC it goes to the analog input to the DSP, which is connected to the Opel RT. We were talking about these three modes: mode 1, 2, and 3. Mode 1 is a direct connection to the supply. There is no safety, special safety. Mode 2 is having portable chargers. Portable charger special safety system is available in the cable and public and domestic sockets. This is applicable. This 3-pin type 1 and type 2 are applicable for AC system between 2 kilowatt to 22 kilowatt. And third one is the EVSC, electric vehicle supply equipment. Supply equipment, it is permanently connected to the network. It is wall mounted commercial automatic charging station. And mode 4 is DC fast chargers. DC fast charger work from 2 kilowatt to 200 kilowatt plus, where we have charging combo to N type 2. And this is the architecture of the EV charging system. You see EV is there. There is a communication between the EV and the EVSC. And there is a communication between EVSC and the CMS. From the CMS, it goes to the home via communication. Central management system. The EVSC connects the charger to the main supply. It offers authentication, metering, payment, and remote monitoring services. CMS is a cloud-based platform managed by company operating the charging station. enables the user-defined apps to help the end user to enables the user-defined apps to help the end user by to identify the nearest charging station or reserve charging slots and make payment. These that was the charging infrastructure. Now different smart charging concepts. Let me some water. There are different smart charging concepts. The different smart charging concepts are there, and one is uncontrolled. What we can say smart charging. Non. These are smart charging concepts. Okay. Some control is there, but there is one uncontrolled. There is no control over the charging process. So that has impact on the network. Sometimes the smart charging concepts, time of use pricing without automated control, basic control on your bi-direction control. This is called vehicle to grid. But in bi-direction, there are many vehicle to grid is one, vehicle to home, vehicle to building by, and vehicle to load vehicle. All these are fall under bi-directional control, and then last one is dynamic pricing with automated control. Then the last week we discussed, the last lecture of the week 9 was hierarchical control of hybrid AC-DC microgrid. Here we discussed components in a hybrid AC-DC microgrid, structure of hybrid AC-DC microgrid, need of storage in microgrid, and management of microgrid. In component, there are physical and communication. Then structure AC coupled, DC coupled, and AC hybrid. Need of storage in microgrid we have that is we have already discussed. Management of microgrid can be two types, power or energy. Power management is to affect instantaneous operation conditions. Energy is to have optimal demand generation balance with emphasis on desired longer term outcomes. Classification of control can be centralized, decentralized, or distributed. Here we see the three types of control: centralized. In centralized, we need a communication network. There is a central node or operator, and there is an access to the global variable. The problem of single point of, however, these are the disadvantage of the centralized system. First is the problem of single point failure, and second, it is not reliable because of this. Decentralized, we have communication network. It is not required in case of decentralized. Control through only local variables and global variables are inaccessible here. Distributed one has distributed is in between centralized and decentralized. So in decentralized, There is no knowledge about the global variables, and it only controls the local variables. While the centralized works, its global variables are visible and communication network is needed here. In decentralized communication is not needed. So in distributed communication network is needed, but there is peer-to-peer communication. There are lesser communication channels and centralized control. And there is no problem of single point failure. And we can access all the global variables. Moving on to question, we already discussed many of these questions. So let us start. What is the purpose of the bleeder resistance connected across this number circuit? First, to discharge stored energy in capacitor when the inverter is not in operation. Second, to store energy from capacitor when inverter is in operation. What do you think? So option A is correct. To discharge the stored energy in the capacitor when inverter is not in the operation. Purpose of snubber circuit in parallel with each IGBT module is to protect against high DVI. Which of the following control loops are there in grid connected PV generation and fitting and true grid synchronization in and current control all the three? Select the correct option before DC link capacitor. It should have higher. The rate should be rated more than the peak grid voltage. Yes. Sorry. We were here. Question. Yes, which of the following control loops are there in grid connected PV generation? MPPT control is there, it is must for wind as well as solar, then inner current control loop is there. Then the grid synchronization loop is there, it is the PLL. Here we are talking about the PLL by. All of three are present in the grid connected tree PV generation. Then just so we have all the three available. All the three control rooms are there in the grid connected PV. Again the same problem. Let me share the PDF now. Okay, I will share the PDF now. Yes, so distributed is already done and we were on the question. Yes, so these three control groups are there in grid. Sorry. We need to select the correct option for DC-link capacitor. So the correct option is that it should be rated more than the peak grid voltage. This is very important so that the active power can flow. The answer here should be that it should be rated more than the peak grid voltage. That should be the answer here. The next question is identify the correct statement. Yes, so next question is identify the correct statement with respect to the solar energy. So first is it converts the variable AC power from PV panel into fixed AC. So this is not correct because the PV panels generate DC power, not AC. Second, it can operate only in grid connected mode. That is also not correct. It can operate both in grid connected and the isolated mode. Third, it cannot provide grid support services. That is also not correct. So none of the above is the correct answer. The major factors to determine for performing active cell balancing are balancing strategy, converter topology for cell balancing, and mode of charge distribution. All of these. What is the full form of CHI controller? Hardware in loop, converter hardware in loop, controller hotspot in loop, converter hill clamping loop. None of the. So controller hardware in loop is correct option. Which of the following is correct with respect to DC fast charger? It is placed on board the EV. Requires thin cable to allow high charging current without cooling. Fast charging operation is done in constant voltage mode. No. Fast charging operation is done in constant current mode, and once it reaches up to 80 to 85%, then control voltage mode is used. Answer, yeah, we will see. The answer is correct, none of the above. So here we need to see the DC fast charger, how it works. So here we have this electric vehicle and here we have the EV, DC fast charging stations. So DC fast charger is not on board, it is off board and it's a big charger. On board charger are small because we need to save the cost and we need to reduce the what we call it, the weight of the vehicle. The input supply here is 415 volt AC supply, and this AC goes to the rectifier which converts it into DC, and then we have the AC-DC converter which provides us the variable DC supply, and then CCCV charge to charge the battery via the protection circuit. Battery monitoring is done by the BMS and which provides the control signal to protection circuit as well as it communicates with the power control unit through the charge controller. Here, to de-energize the EV connector to stop the charging process in event of faults or improper connection. Communicates with EV charging station to control voltage and current delivered to the battery to operate the protection circuit. So what is the function of safety interlock here? The safety interlock, it de-energizes the EV connector and it is there to de-energize the EV connector and it is there to stop the charging process in the event of faults or improper connection. And the protection circuit is the BMS communicate with the charging station to control the voltage and current delivered to the battery, and it also operate the protection circuit. Those two things are very important here. One is safety interlock and another one is the BMS. BMS we have already seen there are so many functions. Uh, Battery management system. It monitors everything. It is helpful in visualizing the output, visualizing so many things, and it is also very important in doing Other things like monitoring of the state of charge, state of health of the battery. Then this safety interlocks are used to de-energize the EV connector, and it's also used to stop charging process in event of faults or improper connection line. Then the BMS, what it does is it communicates with the charging station to control voltage and current delivered to the battery. Communicates with the charging station to control the voltage and current delivered to the battery, and it also operates the protection circuit. Higher current results in higher losses in the charger, and which results in battery degradation. These are the disadvantages of the DC fast charger. Because of fast charging, it is of a huge rating, the currents are higher. Because of higher currents, there are I square losses in the charger as well as the battery. And because of that, there is battery degradation, the degradation of the battery capacity. Then another problem is that high C rate reduces the battery life. Due to heat, there is increased degradation due to temperature. And when fast charging, SOC is reached only up to 70 to 80% due to the lag between voltage and SOC. Because of the lag between the voltage and SOC, the SOC reaches only up to 70%. Therefore, the fast chargers are first operated in the current control mode, and then in the not the constant current mode, and then into the constant voltage mode. In fast charger, the thicker cables are required to allow more current. Okay, this was correct. Which of the following is or are advantage of smart charging? First one, more hosting capacity for distribution network operators. Yes, this will happen, right? Increase in system peak load. No, it should reduce the system peak load. And time of use, tariff optimization, and demand charge management for building managers. More hosting capacity is correct. To answer all of, not all of the above, it will not increase system load. The answer will be here A and C. Because it does the charging in such a way that more and more electric vehicles can be accommodated. That's why boosting capacity increases. So next question is select the correct option with respect to importance of energy storage in the microgrid. So what are the first option is energy storage are critical to enable standalone operational microgrid correctly. Standard energy storage smooth the microgrid power during its connected operation. Yes, both are correct. So in the grid connected operation, it can provide different services. Call it improvement, voltage and frequency deviation, all these things. And these energy storage are very critical in standalone mode because standalone mode there is no other source of energy, and if renewables are also less, then storage needs to accommodate it. During daytime, when the excess renewable is there, the storage needs to charge and dissipate or deliver that power to the load during the evening hours when the renewable is not there. So both answers are correct here. The energy storage are of two types. One is capacity oriented energy storage, one is access oriented energy storage. So here access oriented energy storage is having fast response time. So it can access very quickly. So they are important for for addressing the short-term disturbances. They provide high frequency component of power. For example, flywheels, supercapacitor, and SMES, superconducting magnetic energy storage. These are the options for the access oriented energy storage, which have very fast response time and short-term disturbances, which provide high frequency component of power. Then we have capacity oriented energy storage, which have slow response. And the long-term energy balance, they have slow response, so they can provide energy, long duration discharge. And they will be helpful in buffering out the low frequency power oscillation in the DG outputs. They compensate intermittency of renewable sources in microgrid. The example for this are batteries, compressed air energy storage, pumped hydro storage, hydrogen, etc. Now we have next question is to select the possible configurations of hybrid AC-DC microgrid. AC coupled hybrid microgrid, DC coupled hybrid microgrid, AC-DC coupled hybrid microgrid, or none. So A answer option is A, B, C. The structure of hybrid AC-DC microgrid, there are total three options. One is AC coupled hybrid microgrid. AC coupled. So here the DGs and SCs are connected to the common AC bus. The distributed generators and storage elements are connected to common AC bus through their IFCs. Interfacing converters through their interfacing converters. Then DC coupled, here the DGs and storage elements are connected to the common DC bus, and the interfacing converter is used to link the DC and AC buses. AC-DC hybrid coupled hybrid microgrid. Here the DCs and SCs are connected to both DC and AC, and buses are linked by interlinking capacitor. Which of the following is not correct by about the interlinking capacitors? So you need to find out. Tell me. Interlinking converters and back-to-back converters are two types of interfacing converters. Interlinking converters are single-stage three-phase inverters. Back-to-back converters are single-stage three-phase converters. And interlinking converter is bidirectional. So here we see interfacing converters. The interfacing converters are of two types. One is interlinking converter, another is back-to-back converter. The interlinking converter are single stage three-phase inverters. They are bidirectional And their purpose is equalizing the DC side per unit voltage with the AC side per unit frequency. Back-to-back converter are dual-stage converter with three-phase inverters, and their principle is constant power mode with respect to both AC and DC bus. Next question is two categories of microgrid management strategies are power and voltage, power and current, energy and voltage, energy and current, power and energy. So power and energy management. So these are the reference. We will go through it. This part now, which I just touched upon, but I didn't tell you in detail. Okay, we will discuss that DQ frame. We already discussed that little bit, but I will discuss that again here. What is required here? So we already discussed that for this PI converters. Just a minute. So I will share this with you. So I provided the reference in the book, but I will tell you this. So what we have is here, we were talking about that. Why do we need the DQ frame of reference? Okay, so you were here. Yes, I can use this book directly. That would be much better for you to understand. Instead of me writing everything, directly I can show you using this book. So here you can see so phasor can be represented as alpha beta. So alpha beta is also called we have alpha beta and DQ frame of reference. This is called stationary frame of reference, and this is called rotating frame of reference. Stationary frame of reference and rotating frame of reference. When we convert these three-phase quantity ABC, let's say voltage and three-phase current, we have IABC into this rotating the stationary frame of reference, then we get two components I alpha, I beta, which are also rotating. But if we use this rotating frame of reference, then we get two component ID and IQ, which are stationary. So here the signal assumes stationary, and you can see here you can see we'll give some examples also. Yes, this is the figure. Okay, so this is the space phasor, which is composed of all the three phase quantities. And alpha beta, if you can decompose it cos and sine, this is alpha, this is beta component, this is, and then here you have D and Q. This alpha beta frame of reference is a constant. This is not moving, but this D frame, DQ frame is rotating with this omega t speed. And this space phasor is also rotating in omega t, so both are rotating at the same speed. Therefore, with respect to each other, they are stationary. That's why this DQ frame of reference and because the DQ gives us the constant values, here you can say, let us read this. This is very good. You can see the control in alpha beta has a feature of reducing number of required control loops from 3 to 2. However, how it is reducing number of control loops from 3 to 2? Because in the space phasor we need control of each for A phase, B phase and C phase. But here we need only two, one for alpha, one for beta. However, the reference, feedback and feed forward signals are in general sinusoidal function of time. Therefore, to achieve a satisfactory performance and small steady state error, compensator will need to be of high orders, and closed loop bandwidth must be adequately larger than the frequency of the reference commands. Consequently, the compensator design is not a straightforward task, especially if the operating frequency is variable. So solution for this is offered by a DQ frame based control. So in this, the signal assumes DC waveforms under steady state conditions. Under steady state, you have to note this. The steady state condition is achieved by the PLL. And this in turn permits utilization of compensator with simpler structure and lower dynamic orders. We can use a simple PI controller. Moreover, zero steady state tracking error can be achieved by including integral terms in the compensator. A DQ frame representation of a three-phase system is more suitable for analysis and control design tasks. For example, the ABC frame representation of a salient pole synchronous machine includes time varying self and mutual inductances. However, if the machine equations are transformed to a proper DQ frame, the time varying inductance manifest themselves as a constant parameter. And the DQ frame representation and control of signal system are discussed in the following. So this is very important thing. Okay. DQ frame of you can refer to this book again. DQ frame of reference is very important because it makes our job very easy. We are able to use unconventional PI controllers. Otherwise, we will have to, if you work with the sinusoidal quantities for individual A, B, C phases, then we need to work with the proportional resonant converters, the PR converters. And they are very complicated. They are higher orders, and that's why it's very convenient to use a DQ frame of reference. It makes a job very simple. So it was very important thing. So let us finish this talk today, and we will continue tomorrow. Is next week, same time from 6 to 8. We'll again continue. Thank you very much for joining.